Solving the Solar Coronal Heating Problem Through Radiative Saturation Geometry. Author, Paul Z. 1. Introduction. The solar corona reaches temperatures exceeding 2 million Kelvin, vastly hotter than the underlying photosphere, which is only ~6000 K. This long-standing discrepancy, known as the coronal heating problem, has persisted for over a century. Traditional models, such as wave heating, nanoflares, and magnetic reconnect ion, propose indirect mechanisms requiring complex energy transfers through plasma instabilities. However, these models face inconsistencies with both observed spatial distributions and the directness of heat delivery mechanisms. This paper presents a new solution grounded in observable physics, free-floating atomic saturation by geometric exposure to radiative energy from the solar disk. This model avoids speculative mechanisms and instead focuses on the solid angle exposure of atoms above the solar surface and their ability to accumulate radiation energy over time in the optically thin plasma of the corona. 2. Conceptual framework. The foundation of this model is based on the following principles. Geometric exposure. As altitude increases above the photosphere, a free-floating atom is exposed to a wider field of view of the solar disk. Radiative saturation. Isolated atoms in a low-density plasma can absorb radiation from all visible angles without significant interruption. No collisional conduction in the corona. Due to extremely low density, conduction is nearly non-existent. Heating must therefore come from radiation. Atomic heat retention. Atoms retain heat via internal electron orbit compression and frictional behavior, releasing energy only slowly through radiation. This model proposes that each atom in the corona heats up according to its angular exposure to the solar disk, eventually reaching a maximum saturation temperature determined by energy input and dissipation rates. 3. Geometric saturation model. Let an atom exist at a height above the solar surface. The solid angle subtended by the sun's visible disk from that height is where? Solar radius. Height above the photosphere. The total power absorbed by an atom depends on its exposed solid angle to the solar disk and the spectral irradiance of solar radiation. Where? Atomic absorption cross-section. Planck irradiance spectrum at the solar surface temperature. Each atom reaches a thermal equilibrium temperature when the absorbed power equals the radiated power. Equating absorbed and radiated power gives. Solving for. This result demonstrates that temperature increases with altitude until the full solar disk is visible. At greater distances, saturation occurs and then eventually drops off due to geometric reduction. 4. Comparison to existing models. Model. Mechanism. Unlike the others, the radiative saturation model is geometrically consistent, observationally supported, thin corona, gradual heating, physically self-contained, requires no external transfers. 5. Atomic saturation behavior and internal heating. To support long-term thermal stability in atoms. Internal friction model. Electron orbital compression under high-frequency radiation results in atomic self-heating. Photon saturation limit. Atoms cannot radiate energy faster than they absorb once full solar exposure is reached. Atomic orbit shrinkage. High-energy photons decrease orbital radius, increasing electron speed and friction. This creates a sustainable heat retention mechanism for individual hydrogen atoms and light ions in the corona. 6. Observational predictions and confirmation. Altitudinal peak. Heating peaks at ~1.3 solar radii where reaches its maximum. Optical thinness. Corona's low density means nearly all photons reach free-floating atoms. Ionization consistency. Highly ionized Fe and He lines match the calculated. Temperature plateau. Beyond peak exposure, temperature flattens or drops, also observed. 7. Conclusion. Why this is the best model. This model solves the coronal heating problem by avoiding speculative magnetic processes, using observable, testable, and quantifiable physics, providing a mathematical framework consistent with solar spectral irradiance and corona geometry, matching observed temperature profiles and ionization states without requiring dense matter. Final claim. The The solar corona is hotter than the surface not due to exotic field behavior but because of a simple, elegant truth: atoms in the corona absorb more radiation from the sun than atoms on the surface because they see more of the sun. Appendix, constants and definitions. Emissivity of hydrogen (1) for fully ionized gas. Integrated over 100 to 300 nanometers UV peak for maximum absorption. Effective cross-section for UV photon absorption. Future work. Refined measurements of at various solar distances. Experimental laboratory analogs with hydrogen in optically thin UV chambers. Comparing emission line spectra to predicted curve across coronal heights.